Hi guys. Okay, so this is going to be a review of an explanation for the practice quiz. So I just want to start a little bit by describing a little side topic I talked about in the review session, which was how acids and bases are used to dissolve things. So we use acids and bases as cleaning products all the time. And I went down a rabbit hole last night of like a post from post asking, what is the difference between how acids and bases um, work for chemical burns, how they burn in different ways, and which is worse, and stuff like that. And it was really interesting. So acids, how they work is this kind of coagulative necrosis where they break down the proteins, but once they've done that, let's say on your skin, they kind of just stop because they can't really penetrate further, and they just sit on top with all this like dead, you know, and messed up protein layer. And base, on the other hand, will keep going until it neutralizes itself. So it's much more dangerous. And what the phrase someone said was, an acid will give you a burn, but you can lose a limb with a base. And the way that the base works by dissolving you is through this like liquefactive necrosis, basically by reacting with the lipids in your membranes of your cells. It turns you into kind of soap, and so it just keeps going, and usually you don't even feel what's going on, and then that's why it's so dangerous. But yeah, there are people who've used these to try to get away with murder, and one of them was from good old Chicago over 100 years ago. This guy murdered his wife and then dissolved her in lye, which is like an alkaline or basic product, but really interesting. Yeah. Okay, so we'll start with a mock quiz now. And so the first question, we're looking at a strong acid. Okay, so make sure you memorize those strong acids and bases. Okay, so all we need to do here is the negative log of this concentration, because the concentration of HI, all the HI will dissolve, become H3O plus, which is the same thing as H plus. And remember the formula for pH is just this. So we can directly input that value. And then when we solve for that, we'll get negative pH, okay? And you might be asking yourself, that's weird, I've never seen that, but it's okay. And that just means it's super acidic. Usually the range for pH is, 0 to 14, but it can definitely be negative or over 14 as well. Okay. And then the next question is asking just about what kind of functional groups we see here and which is not found in the molecule. Okay, so we see our two benzenes over here. So we got benzene. Alcohol, we see some alcohols over here. I'm gonna skip C for now. And then carboxylic acid we see over here. And then the amide right over here, okay? There was some confusion with what defines an amide. Basically, an amide just has kind of this structure where the R's can be anything, but really what's important is having that double bonded OH, or sorry, that double bonded oxygen with the nitrogen right next to it. Okay. All right. And then, so we have everything here: alcohol, carboxylic acid, amide. But what about this? Okay. So if you saw my review video, I went over a little bit about what the difference is between primary, secondary, tertiary, and amine. So a primary amine would look something like this. It would be a nitrogen, and then it would have only one R group. So that's why it's primary. The rest would be hydrogens. Okay. Secondary amine group would have two R groups. And again, those R groups just represent anything coming off of the of the nitrogen that's not a hydrogen. And then a tertiary would have all three as R groups. Okay, so what we see over here is actually a tertiary amine. Okay, that's why C is wrong. All right. The next question is asking, we're looking at rankings of acids and bases. This one is specifically saying fourth most basic conjugate base. Okay. How I always approach these problems is first rank them from strongest to weakest acid, because otherwise it gets too confusing. And then if I want to convert between strongest, weakest acid to a base, like how it relates to a base, is I just flip the numbers. But first we have to ask ourselves, what makes an acid stronger? Okay, how do we determine acid strength? And that's really based on its ability to stabilize the conjugate base. Okay, so to stabilize its future self makes it more comfortable losing that proton, because an acid, it's defined as something that, you know, donates protons. So if we make it, if it becomes more comfortable losing its proton, then it'll react more and then stabilize that conjugate base. Okay, first way we do this is through resonance. Okay, resonance is just, so this is going to be an R group. Actually, I'll show you right over here. There's some resonance going on here. So if we were to drop this proton, right, it'd be gone, and then some resonance would be happening here. Okay, so typically where we see resonance is from an oxygen with a double bond. And that would do some electron sharing to the other oxygen right over here. Okay. The next thing that can help with stabilizing the conjugate base, making the acid more comfortable letting go of this proton, would be the inductive effect. What that refers to is that those electronegative atoms helping out. But there are three details that we need to know. So the closer they are to the acidic atom, this is the acidic atom. The acidic atom is the one that loses the proton. Okay, it's usually going to be an oxygen that's connected to a hydrogen. It's going to be all of these. Okay. So we want to consider how close is it to the acidic proton. We have to consider what kind of electronegative atom it is. The more electronegative, the more supportive, the better. The conjugate base will be stabilized. So yeah, fluorine is stronger than chlorine, which is stronger than bromine, which is stronger than iodine in electronegativity. Okay, the last thing we need to consider is the amount. Okay, so if we have more chlorines, that's better than having just one, for example. Okay, so if we want to approach this problem, again, the first thing I would do is just rank them from strongest to weakest acid, because that's just what's simpler to me. And then, okay, so if we're looking at all of our examples here, the one I see is the strongest is going to be this one. It's going to be the strongest acid, since it has resonance and it has those bromines as close as possible, and there's two of them. Okay. All right, then the next one I'm going to consider as the strongest is going to be this one. So again, it has true bromines. Even though the other one is further away, it's still better than just having one chlorine, for example. Okay. But this would be my next option. This is going to be number 3. Okay. So we have just one chlorine there. All right. One step lower would be having no inductive effect, just resonance. And then one step lower than that would be having nothing, just the acidic proton. Okay. But we're not fully answering the question yet. It's asking for the 4th most basic conjugate base. So now we need to rank it in terms of base. We're just going to reverse the numbers, okay? So I'm just going to do the opposite of all the numbers. Okay, the 4th most conjugate base turns out to be this one. Okay, this one is going to be some naming. And all right, so if you watch the review, we went over the same steps, but the first step to naming a molecule will be first finding the longest chain with the most substituents, okay? And if we want to look over here, the way we do that is There's two ways actually we can go about this one specifically. We can go this way, or we can go this way. That could be our base chain. They would give us the same answer, and that's okay. Yeah. So then, okay, I'll just go with this one. That'll be our base chain. Okay, and that has, this is a heptane, 7 carbons. So heptane. Okay, number 2, a second step would be figuring out which side do we start from? What do we label as our first carbon? This one or this one? So the way to do that would be to find, which side do we hit the first substituent first? But sometimes we have a situation where we hit the first substituent first on both sides. So the way that we determine which way to go is dependent on 2 things. So it's dependent on where we hit the first substituent first, or the lowest numbering scheme. Okay, the lowest numbering scheme just means, the lowest numbers in our name. So here, if we went this way, it would be 1, 2, 3, 4. Those are the 2 substituents in our name. But if we went the other way, we started over here as 1. This would be 1, 2, 3, 4, 5. Okay, those are bigger numbers. So we're not going to go that way. We're going to go this way. 3, 4. Okay. So then our substituents are going to be 3-ethyl, 4-ethyl. Okay, and we put that all together, we get 3,4-diethyl heptane. All right. Some details I want to emphasize. Some things don't count for alphabetizing. So those things are the S in sec-butyl, or the T in tert-butyl, or the D or just any of the di, tri, tetra, whatever. For example, like dimethyl, the M would count, not the not the D. In isopropyl, though, isopropyl is just one word. The I counts. Okay. Okay. So now this is another conceptual problem. The first one asks how many sp2 hybridized carbons. So the first way to recognize that is where are the carbons with a double bond connected to them, because that's usually where we're going to see them. So I would label it here as 1, here, here, here. Any carbon with, connected to a double bond, that's 8. So that fits. That's good. Okay. The second one is asking, the second one is saying there's 10 hydrogens. I'm actually going to skip that one for now. The third one is saying this molecule contains carboxylic acid and ester group, which is true. So we have a carboxylic acid and an ester group right over here. So that works. D is saying there are 9 carbons atoms in the structure, which is true. So I'll go ahead and highlight them. There's just all of those. I just added this one right here. Okay, so that's true. And then oxygen that's ostracized is going to be sp3. So that's true. So we have 2 lone pairs, and in total, like 4 entities, 4 electron bearing entities. And so that would be sp3. That works. The only one that's false is that there's 10 hydrogen atoms. There's actually, I believe, 8, but let's go ahead and count them. So we want to make sure that carbon always has 4 bonds. Okay, so here's 1 hydrogen, and then each of these carbons need a bond. There's going to be 3 over here. Okay, this is actually 8. So this will be our false one. Okay, so now for number 6, we're looking at a solution of HCN with acetic acid, and we need to find the pH. Okay, so those are 2 acids. And if you remember, I've been saying that we can't mix acids and bases with bases. It's not going to work. So what do? We actually are going to pick the acid with the strongest Ka value. So we're going to pick the strongest acid. The acid over here, this Ka value, negative to the -5, is so much stronger than something to the -10. It's like an Olympic medalist versus a little league player here. Okay, so we're going to go with the acetic acid because the HCN is not going to change the pH at all compared to the acetic acid. Okay, so then we're going to find the pH. The first thing we would do, we decide we want acetic acid. Okay, now this is going to be a weak acid calculation. First thing we want to do, set up that ice table. Okay, so we're going to do 0.795 molar acetic acid minus X equals approximately the same number. So I'm just going to put the same number here. Okay, and then I've set up, this is going to be the same setup you'll usually see. Some change is going to happen, some dissociation is going to happen, and then these will be our products that we don't know yet. Okay, this number is really important over here because it'll tell us, can help us find the pH. Okay, because H3O plus is the same as H plus, and negative log of H plus is pH, right? So, okay, let's do our Ka calculation. So we decided this was our Ka value we're using because we're using acetic acid. So 1.8 E negative 5 is equal to X squared over 0.795. Okay, we're going to solve for X. And then, oh, I just wrote that right here. Oops. Okay, so the same thing is right over here. Okay, and when we solve for that, this is the value we'll get. 1 second. Okay, basically it'll be this. Okay, so that's our H plus concentration, and perfect. We're almost there. We just need to input that over here. Okay, that's basically it. The next question is even simpler. We're just given, this is our HCN in solution. What is the pH? Okay, so we're going to do another weak acid calculation. First thing always to do for weak acid, weak base is to do that ice table, right? So HCN plus H2O okay, so we'll have 1.2 as our initial, so initial value. All right, and our Ka value is 6.2 E negative 10 equals our products multiplied by each other over our reactants. Okay, then we're going to solve for X. Okay, X is going to equal our H plus concentration, right? So we're solving for that. We solve for it. Now this is useful because we can do negative log of this, right? Negative log of H plus concentration will give us our pH, okay? And that's what the answer is. Okay. For 8, it's a little bit trickier because we're dealing with a base, okay? So we have to think about bases in terms of Kb, the OH concentration, and pOH, okay? Then we can convert it to pH, okay? But we have to be consistent, okay, with Kb, the OH concentration, the pOH, okay? Don't mess around with acid stuff when we're dealing with bases. All right, so here we're gonna set up, I'm abbreviating ethylamine as A minus, okay? Because an abbreviation form of an acid here is gonna be an A with, one hydrogen. This would be like the acid form, and then base would be like A minus, it lost its proton, okay? All right, so A minus plus water, it's protonated, plus OH minus, okay? So we start with 0.75 here. So we have, again, products over reactants. to the KB. Okay, so our KB, let me go find it real quick. 5.6 e negative 4. It's equal to the product, so x squared over reactants, 0.75. Okay, and then we're going to solve for x. X, again, here is our OH concentration, all right? That'll help us find the POH. So we solve for x, then we'll find the POH, right? Because negative log of the OH concentration is the POH. Okay, last thing we need to do is convert the pH to the POH, or I mean, sorry, the POH to the pH. We just do 14 minus that. Okay, so that is number 8. For number 9, we're just looking at major species, and yeah, so we're basically dealing with 2 weak acids here. Okay, these actually really look like strong acids because HF kind of looks like a strong acid, but it's not. It looks like HBr, HI, all those, HCl, but it's a weak acid. HNO2 also looks like a strong acid, but it's actually a weak one, right? HNO3 is a strong one, but HNO2 is a weak acid. Okay, that means if they're weak, the dissociation constant is less than 1, which means the forward reaction is not going to be favored. So that means they're not really going to react that much. A small percentage of the acids are going to react with water. Okay, so that means most of them are still hanging around. If we had HCl alternatively, then almost all of it will dissociate immediately. So, okay, that's why they're still hanging around. And we're always going to have water, right? Water never leaves us. We have an infinite amount of water. Okay. Last problem. It's kind of doing what we've been doing, except a little bit backward. Okay, so you have to be comfortable doing a reaction, or sorry, doing a mechanism, or problem solving forward and backwards. So here we have the pH, but we're solving for the Ka of an unknown weak acid. Okay, so we have our concentration of the weak acid, we have the pH, and we just need to find the Ka. Okay, so we have a good amount of information. We have enough. We can solve for Ka. First thing I would do is kind of set up an ice table. All right, so I'm going to abbreviate our weak acid as HA plus water. Okay. So Ka is going to be equal to x squared products over reactants, right? So products multiplied by the reactants. I'm sorry, products multiplied by each other divided by the reactants. Okay. We don't know x. Okay, so we have 2 unknown variables. Okay, but we can find x. We can find x using the pH. So the pH, real quick. Okay, so x is the H3O plus concentration, which is the same thing as the H plus concentration. So x equals the H plus concentration, which equals 10 to the negative pH. So the negative pH here would be 2.737. Okay, when we solve for this, when we solve for x, we should get like 0.0018. So yeah, we just solve for x, and then we'll put that back in here. We'll square that. We'll divide it by 0.607. We'll get the Ka, and this is what you should get for the Ka. Okay. All right, so that's pretty much it. I hope this was helpful, and yeah, I will see you soon.